Okay, chapter 4. Chapter 4 is what's called linear regression. We just got to review linear equations, which are equations of lines. Linear equations in statistics. Technically, a lot of this is going to be a review of previous math classes where you dealt with lines. Okay, a linear equation. Let's review the concept. Is an equation of the form, and the variables might change. They might not use y and x always, but for the explanation we'll be sticking with y and x for now at least. The equation of the form. It has a particular form. Y is equal to ax plus b is sometimes the way they write it, where I'm not ready for that. Or y is equal to a plus bx. It's a different way of writing it. The y and the x are variables. Well, that's part of my explanation, but the a and b are real numbers. So the a and b are going to be filled in with numbers, fixed numbers, constants. And they're called the coefficients. And that term will come up again. And the x and y are called variables, but more specifically they have very specific names. So when it's this form, x is called the independent variable. And y, which is by itself on the left, is called the dependent variable. And there's actually other terms for this. X's could be called the independent variable, or sometimes it's called the explanatory variable. Don't write that down because I'm not going to use that term. Y is called the dependent variable, but also the response variable. Don't worry about that, but there are other terms for it, but the most basic one is dependent and independent variable. One more bullet point that I don't think I can fit there, so I'm just going to come up here. The coefficient of x, or the independent variable, because the variables, the x and y could change to other letters, but again, for now we're going to stick with the coefficient of the independent variable, or x, is the slope of the line. And that'll have a particular meaning, which we will get to later in this section. But let me pause and just go back a little bit. First of all, back in algebra, they often would use y is equal to mx plus b. I'm not sure why they chose m to do it there, but in stats they tend to use a and b, and interchangeably. So when you go to your calculator and we start doing things with it, you will see some formulas like that and some formulas like that. Different textbooks will have it differently. So, but you just have to be aware that it's going to be of the form y is equal to some number times x plus some constant term. And they may switch the order, or they may do different things with it, but it's still just going to be a y, an x, a constant, and a coefficient of the x. They don't use m anymore. And so what I usually do in class is make sure we know which one is the slope, the coefficient of the x. So in this equation, this form of it, the slope is a, because that's the coefficient of the x. In this one, which is written differently, the slope is going to be b. So they're not consistent with where they put the a and the b in stats, but as long as you can identify which one's the slope, you're okay. Let me go through an explanation about dependent and independent variable. Don't write this down, this is just a half-assed explanation. Essentially, when you plot points, you're used to basically picking your x's. which, yeah, so you pick an x and 1, maybe in algebra they would often use nice whole number integers. We're not going to have that, unfortunately. We are going to have decimals and computations and use our calculator. But back in algebra, when you wanted to graph things, you would pick the x, and then the y that you would fill in here, you don't fill in your own y's. The y here would depend on the equation and what x is. So you would then plug it in, get a y, and fill it in there and there. So the y depends on x. Graphically, when we start looking at applications, a lot of times we'll look at things over time. And time just marches along from 2018 to again, don't write this down. This is not a formal explanation. I'm going to erase this. My formal explanation is coming. But time just marches along from 2018, 2019 to 2020, independent of anything else, regardless of what's happening in the world and what we're all going through. But I don't want to get into any kind of crazy stuff that's happening this year, but the population may go up. It may be going down after a certain time, who knows? But basically, the population will depend on the year. So again, time is independent, but the population depends on what year you're talking about. That's where the terms come from. But again, don't worry too much about it. If you have years, it's usually the independent. Oh, I should have just mentioned it. Sorry. Okay, anyway, time is your independent variable, and that's like x. That's why x is the independent variable. Whatever is over here happens independently of anything else. Y is a dependent variable, so in this case it's p instead, but the vertical axis is your dependent variable, and again, that will depend on what year you're talking about. Okay, that was all informal, but up to there is your actual formal notes that you will need later on. I'm going to do a quick example of just sketching a line. So a lot of this is a review of previous math classes. So we're going to sketch the graph of our first linear equation. And it's not going to be a nice one with whole numbers. It's going to be y is equal to negative 0.86x plus 42.3. Okay, and our book will actually specify an interval. In my case, I would actually give you the axis. I would give you the graph to work on, so you would already know the interval. But if not, if you actually looked at the textbook that we use, or that we're supposed to be using, they won't have any graph ready for you. They'll just give you that. And what that means is, you're going to make a graph, and your x-axis, which is along the horizontal, you want to span that from 0 to 30. If you're drawing it on your own completely, you would need to get up to 30. So I would go by 10s probably. So similar to what we did in previous box plots and things, you have to scale your own axis. But on the exam for this chapter, exam 2, I'll give you any set of axes that I want you to use. I don't want you making one on your own. If you have to do it on paper, you will have to though. Okay, anyway, I want to graph this line on there from the interval 0 to 30, so I'm going to draw some line going like that, but I need to do it accurately. And back in algebra, you could count rise over run and count 2 up and 3 over and that kind of thing, but you can't really do that with decimals. You're not going to be able to go up 0.86 and over 1 and start at 42.3. That's going to be much more difficult. So there's another way that you are familiar with probably on how to do this. We'll do it together. But that method is plotting points. Ooh, this rag is soaked with ink. It's not cleaning. All right, good enough. All right, but I'm going to stick over here. What you would do is you would, like I said earlier, pick your own x's. Now you don't need to do 3 or 4, you just need 2 points. Boom, boom, and you just draw a line straight through. So all we need are 2 points. At least 2 points, but I'll just say 2 points. 2 points is enough to draw a line. As long as we do them semi-accurately, our line will be semi-accurate. So we'll pick some x's, and it helps you not to do 0 and 1. Don't write it down because we're not doing that, because if you do 0 and 1, what you're going to have is you're going to have a point there and another point right there at 1, and it's not going to be accurate. It could be like that, or it could be like that. You can't really get an accurate feel if the points are too close together. It's much better and much more accurate if you spread them out. So I'm going to go 0, and I'm just going to use 30 as my other point. So now, when I graph, this is not accurate yet. When I graph my 2 points, 0 and 30, there's pretty much one line you can draw. You can't really be too far off from your neighbor. They might do like that, and you might do like that, a little bit off. But so you can tell it's very similar lines. So it's not prone to as many errors if you spread the points apart. But again, if you put them too close together, your hand-drawn graph will be not very accurate. Okay, we've got to find these y values. How do we find them? We plug into there. So go ahead and start plugging these in. I guess, I don't know where I'm going. I'll do it right here. Y is equal to, and I'm going to plug in 0. Negative 0.86. And I'm plugging in x equals 0. And I'm simplifying, and this one is nice, and it comes out to just 42.3. So 0 is always a good one if it's available. Definitely use that and take advantage of the fact that it makes your computations easy, something you can do in your head. Next one I cannot do in my head, so let me go ahead and get my calculator. We're going to plug in 30. Don't forget that negative, and don't forget the negative button on your calculator is not the same thing as the minus button. So make sure you do this, because the negative button, I do want to remind you, I think we've done it before, but it's not the minus button, subtraction on the left right hand column, it's the negative that's below the 3 key. That's a different button from a minus sign. Negative 0.86 times 30 plus 42.3. I got 16.5, yep. And you could have chosen different points for me. Again, try to keep them one on the far left and one on the far right of your graph. So it was 1 and 29 would have been fine, even 0 and 20, but I prefer just as far apart as you can go. I'm definitely not going to mark you wrong if you didn't do that. Oh, I forgot to remember my answer. 16.5. Okay, and I'm going to have to scale my vertical axis on my own, but my high point is 42.3. I'll go to 50s. 10, 20, 30, 40, and 50. Okay, and again, the graph will be provided. Unless you do it on paper, you have to translate that to your own paper. 0 on 42.3. You're staying on 0 for x. I forgot to label my axis y, but let me go ahead and do that. 0 and 42.3. Right about there. Just a little bit above 40. And then 30 and 16.5. 16.5 is about halfway between 10 and 20, a little more than halfway. So about there. And then you would just draw a straight line using your ruler, and hopefully all this is done with a ruler and somewhat nice, but it's fine if it's not. I just want to make sure you know the principle behind it using 2 points. These are 2 points that satisfy and therefore are on this line, and you're graphing the entire line, the set of all points that satisfy that, the set of all pairs of x, y. Okay. Next, we're going to talk about a scatter plot. A scatter plot is a graphical representation of a data set involving 2 variables. We're going to do a scatter plot in a bit, but before we get to that, we're going to discuss a model. An informal, I guess it's not, the book also refers to it as a prediction equation. That's a very rare phrase to hear. A model is very common, so I'm going to stick with model. model is an equation that represents the theoretical relationship so a model is capturing a theory on how two variables are related. So a theoretical relationship between variables in a data set. And it could involve any number of variables, but we're going to be sticking with just two, an x and a y. Let's see. Okay. Now there's different forms of different types of models. Can I fit it? Yeah, I'll fit it here. We are going to be focusing on linear models, strictly linear models in this course. And I'll write the form of it here. I'm going to put a little hat on the y, so I'm going to refer to that as y hat. That'll be a distinction between y hat and y, so I'll just talk about the distinction later. But for now, just be aware that I am making a little hat on my y's. For my models, y hat is equal to ax plus b, that form that we saw before, and that's an example of a linear model. And even though we're not going to do it, I do just want to emphasize that linear models are not the only model. They're sometimes good for certain data that grow linearly and that have simple models. But oftentimes the next most common thing is an exponential model. And that'll be of a different form that we're not dealing with, but I'm going to show it to you anyway. A times b to the x power, where your independent variable is an exponent. So a lot of times when you see data, or you don't have much data, there's a debate between scientists on whether they should be using a linear model or whether they should be using an exponential model. So I'm going to sort of give you a preview of what we're going to be doing. You're going to do a scatter plot, which is going to be basically a set of points on a graph. Oh, I'm going to drop it big so you can see. Okay. That's x, that's y. That's x, that's y. And for a data set that would hint at an exponential model, it would look something like this. Okay, and I'm going to draw a linear model and an exponential model on top of those points. I feel like I didn't draw these big enough. You don't have to draw them as big as I am. I think I just need to do it for people that are watching this on their phone or something. You see that? Yeah, it looks like you can see it. Okay. So if you see data that looks like this, and you want to model it, you want to show how it's growing, and you want to look into the future, what's going to happen in the future, it's probably just going to go that way. And how are you going that way? But you're just imagining a line on there. And we're not just going to imagine a line, we're going to be graphing it, and we're going to be actually computing that line, the slope of it, the a and the b for this line. So that would be your model. Y is equal to ax plus b. You'd have to find a, you'd have to find b to make it go exactly where I drew it. We will be doing that in a later section. However, if you had something like this, which is basically how a virus spreads in a pandemic, it starts going up, they say it grows exponentially, meaning it's not just steady growth, it's just going to blow up at some point and create a crisis for the people that have anything to deal with it. But anyway, that would be an example of an exponential model. We're not going to be dealing with it, but it is something that will come up in real life situations. But we're going to get a feel for models using the simpler version of linear models. Okay. So now I am going to talk about that y hat. This is important. It applies to any model, but specifically linear that we'll be dealing with, but We need to know the distinction, as I mentioned, between y hat and y. There are two different things. Y hat is a predicted value according to the model. Predicted value is the term we're going to be using. Y is the actual or observed value. Okay, and so the prediction and what's actually observed are not always the same. Sometimes you predict things are going to go well for us and it goes badly. Sometimes you predict the temperature is going to be a cool 80 degrees and it turns out to be 100 degrees. So sometimes your prediction is off from what ends up actually happening. How much it's off by is something we're going to be dealing with, and that coming up here, that is called the prediction error. A fancier term that actually the calculator uses, it abbreviates it, RES, but so there's a more abstract term called residual. It may come up in a future math class. I'm not using it. I'm going to use a simpler, more self-explanatory term, prediction error. But be aware, residual is a common term that they use instead. Is the difference. Did I put signed? I didn't put signed in my notes, but I'm going to put it here because I do want to emphasize it can be negative or positive. I'll put it in parentheses. So it'll be a negative or positive prediction error, so I'm going to put that signed between the predicted value and the observed value. So exactly what I was just talking about, the fact that the prediction may not match up with what we actually see in real life. Okay, the symbol for it, I'm going to give you a formula for it. E, that's your prediction error. And it has a particular order, y minus y hat. So when you do this, when you compute the prediction error, you have to look at your notes and make sure you are subtracting y, the observed value, minus y hat, the predicted value, and get the correct sign. If you do it the wrong way, you get the wrong sign, and technically minus 2 points off of that problem. So follow that order. We'll do examples in a bit. We're getting to it. I'm going to pause here because in case I F up this up and I got to redo the whole video. Okay, let's start working on an example and get familiar with an actual example and get familiar with all the concepts we just talked about. The data below gives the ages, or the age and weight of a growing kid. Weights in pounds, age obviously in years. 2, 6, 8, and 11. So for some reason they only measured this kid's this kid's weight at irregular intervals. Okay. We start off and make sure we understand independent and dependent. Which is the independent variable? And which is the dependent? Sometimes it's debatable, but for the examples that they make you do in a class like this, they tend to be pretty obvious. And I did not leave enough space for my answer. Okay, so you can think about which one is not affected by which one depends on the other. More commonly, I would say think about how you would graph it, a typical graph. Would you put the weights over here? Don't write this down because I don't agree that we would put the weights over here. He doesn't weigh 120. 20, 30, this is a completely made up graph that we're not going to stick with. And here's your weight. And then here's your ages. Is that a reasonable graph? Think about if that's how you would do it. You want to see this kid grow over time. And so you probably not put it this way. You don't say, when he was 20 pounds, he must have been that age. More likely you will see the age along here, time going along here, and then we'll see his weights going up or down. So you instinctively, I'm going to cram it over here, would want to put time along here, so the age. And therefore that's like x, that's an independent variable. The kid just ages along and nothing's going to stop that, nothing's going to speed it up or slow it down. But as he ages, he starts to grow and his weight depends on what age he's at. Alright. Anyway, that's usually what you think of when you want to make the distinction. So meaning age is like x, weight is like y, and therefore age is the independent variable like x, and weight is the dependent variable. And that's enough. I have a couple of problems like that on the homework that I just want you to get familiar with the concepts. We're not stressing it too much. Again, there are situations where it is debatable, but that one is fairly straightforward and obvious that you do want to see the age and time marching along and going to he's a teenager and an adult and his weight going up or down as he diets and eventually becomes an adult. Okay, next. Leave a lot of space in your notes because we're going to do a big graph and I'm going to show a lot of detail here, so I'm going to draw a big graph for this one and I'm going to cram all the rest of the problems on that left side, but I want to have a big graph that you can see clearly and see a lot of detail to it. Create a scatter plot for the data. And sketch the model y hat is equal to 7.2x plus 5.6. And I'll specify, it might have been easy, for the context it might have been easy for us to use A for age and W for weight, but I do want to just go back to y and x temporarily, but I'll make it clear, age is going to be like x, weight's going to be like y, and I didn't specify it here. Just to get us, used to these concepts with our more familiar y and x. You will be dealing with other variables later. It shouldn't be too bad, but definitely want to stick with y and x here since we are familiar with it coming from a previous class. Okay, we get two things to do. We have to create a scatter plot for the data. We're going to do that first one. And then we also want to sketch the model y hat is equal to 7.2x plus 5.6. First of all, note it's a linear model because it's of the form y hat is equal to ax plus b. The a is 7.2, that's your slope. 5.6 is your b, or your constant term. That is a y-intercept, if you remember from algebra. But if not, no worries, because we're just going to be plotting points to draw it. We're not going to do rise or run and using the intercept necessarily. Okay, what are we doing? All right, here we go. We're going to scale it on our own, but again, on your exam, you'll have a graph provided, so you'll know how to scale it. I'm going to go by 5s for the age. We will call that x. And then the weight I'm going to go up to 120 by 20s. 20, 40, 60, 80, 100, and 120. That's going to be our y. Okay, again, we're doing two things here. The scatter plot is first. And the scatter plot is just plotting these four ordered pairs, or these pairs of data. So 2, 32.6. When the kid was 2 years old, they weighed 32.6 pounds. You just eyeball where you think 2 is, and you eyeball where you think 32-ish is. So about 30, slightly above 30. So about there. In real life, you would do this in Excel or something, some sort of software to do it accurately, but here we just want to get a feel for it. Age 6, 45.1. 849.0. This is barely above. And 1191.4. Okay, we're keeping it simple with only 4 points. You might have slightly more for your assignments and your problems that you're going to be working with, but we're going to keep it simple here. Okay, that's part of the problem. We now want to sketch the model. Y hat is equal to 7.2x plus 5.6. We want to do it somewhat accurately. And we're going to do it by plotting what we did earlier, plotting 2 points. It is technically separate from the scatter plot. Oh my god, I need that. I've got to move it anyway. You have it in your notes, but I need it up here, and why am I writing y there? God damn it. Make sure you can see that because I'm going to be referring to that, but I do need to cram it up there so I can have space. I'm going to leave this up the whole time almost. Okay. Oh, I'm going to cram it here. And then erase it almost, and I'll cram it over here. Again, I'm trying to figure out how I'm going to use the space. I'm going to make a little table, and I just need 2 points to do my model. I'm going to pick my x's, one on the far left and one on the far right. And I'm going to find the corresponding y hat. Now, there's y and there's y hat, and there's a distinction between this. That's the data, and it's the scatter plot that is based on those. This y hat is based on this equation, which is technically separate from the scatter plot. And it is given as y hat. We'll get used to the distinction in a bit, but notice I am putting y hat here, because these are going to be points on that model, not the kid's actual weight at any point. Okay, but let me start with age 0. The far left of the graph, and I'll just go to 15, I guess, or I mean I made it a little bit longer, but yeah, 15 is good. You could do 20 if you wanted to, if you made 20 on there, if you have enough space for that. Oh, what am I doing? Okay, and I'm not going to write it, but I'm plugging in 0, oh maybe I should. I'm plugging into the model. I'll do it over here, but I'm going to erase it. So we're doing y hat is equal to 7.2 times 0 plus 5.6. That's 5.6. Y hat is equal to 7.2 times 15 plus 5.6. That one I have to use my calculator for. Why did I feel like that's wrong? What did I just do? Oh, that's right. 113.6 pounds. Okay. And now I'm going to sketch the linear model. That model y hat is 7.2x plus 5.6. I don't want to use my black pen and do 2 circles, because then if I get called away to my DoorDash order and then I come back, I might forget which one is scatter plot and which one is my points on my line. So to distinguish, it's not necessary, but I like to draw it separately. First of all, I have different colors, but if you don't, I'll use an X for this. So 0, 5.6 is about here, and I'm going to use an X. and then 15 and 113.6. Here, I'm going to use an X. And then you're drawing a line between those two X's. Irregardless of the scatter plot, it's technically, as of now, unrelated to that. It may not hit any of the points. It may be way off from the points. So you are just connecting the X and X from the 2 points that are on the model. That's, again, separate from the scatter plot. Now, they are related in the sense that I came up with this model as an attempt to see how this kid is growing and use it to make predictions about how much he's going to weigh when he's 20 years old and so on. How did I get this model and how did I get it so perfect to be very close to the points? That's the next section. Don't worry about that. Just for now, you rely on me to give you models that are fairly accurate, but later on you are going to learn how to come up with that model on your own that models this kid's actual growth. But that's for later. We just got to get familiar with general concepts. And so let's start moving on to part C, which I'm going to cramp here. Yeah, I'm running out of space here. According to the model. What was their weight at age 13? So an important phrase there is according to the model. Here's your model. Again, the points have nothing, I mean, they're not directly related, so you're not looking at the points, and we don't even know what he weighed at 13 anyway, so you are looking at the model according to this. According to the red line, we're not going to do it off the graph, although we could. If we did it off the graph, what we'd be trying to do is, if we had a super accurate graph, we'd go to 13 years of age, and we would ignore the black dots, and we would go to the red line, because that is the model, and it's asking us according to the model. And then we would go over and estimate what that weight is. 99-ish? I don't know. But a hand-drawn graph, as beautiful as I made it, is still not going to be as accurate as using your actual equation. So we're not going to rely on a hand-drawn graph. We're going to use equation. The model is y hat is equal to 7.2x plus 5.6. And what we want to do is we want to predict their weight, essentially. And that's where these terms of predicted model, or prediction model, and prediction error, and that kind of thing come from, because we're trying to make a prediction about what's going to happen with this kid at age 13. That's your x, 13 years of age, you plug it in, and you get your corresponding y hat. We got 99.2. Hey, my graph is pretty good. I said 99-ish. Actually, I knew it was 99. But it was pretty close. What are my units? Pounds. Because that's weight. Keep that in mind. X is age in years. Y hat is weight in pounds. Either actual weight or predicted. That's a predicted weight according to the model, the red line. D. According to the model, at what age will they reach 125 pounds? Think about that. Again, it's according to the model, so you ignore the table, you're looking at the red line. You could, in theory, get a half-assed estimate off of your hand-drawn graph. If you try to do that, you'd go to 125. This is your weights, which I forgot to label. Maybe I should have labeled it so I know, but you know for sure this is weights. And I'll go to 125 now. And I'll go all the way over, and thankfully I made my, I got to extend my graph a little bit, and then I would make a prediction about there. But again, that's not going to be as accurate as using the equation. So let's go ahead and use the equation. Thinking about where we're plugging in at 125. Keep in mind what's x and what's y. Y hat is equal to 7.2x plus 5.6 is our equation. I'm going to erase and fill in the 125, but I want you to make sure we know where it's going. X is age. We want to find the age. Y hat is a predicted weight, and we want to know, we're going to use 125 there. So we're plugging in 125 for Y hat, and we're going to predict when he's going to reach that weight by solving for X. You got to subtract 5.6, then you got to divide by 7.2. I'm not going to belabor solving equations. We did it in chapter 3 with the Kung Fu Panda problems, specifically so we could get familiar with it. And then divide by 7.2. Okay, I'm skipping a bunch of steps and I'm getting 16.7. What happened? My answer's not matching with that. No, that's fine. 5.6, right? 6. I think I messed up on there. Okay. Now, if you're estimating age, in theory that's 16 and a half years old, but we don't really go with that. So you can round the usual way to 17 years. I'm not super picky. You can leave it like that too. 17 years old. Oh, that was pretty good. I would have said 18, but I was wrong for my hand-drawn graph. This is a more accurate answer. 17 years is when this kid will reach 125 pounds according to the model, the red line. Okay, now let's get into it a little bit more. Make sure you get that down if you need it. I want to have this graph clean because I'm going to be drawing more on it and using this for more explanations, so that's why I drew it big and that's why I'm struggling to make things fit on this. Where was that? Oh man. A, B, C, D, E. Real quick. We did one similar to this, but here it's I want to talk about this one because according to the model is again a crucial phrase. According to the model, the red line, what was their weight at age 8? I want to mention, we know their weight at age 8 was 49 pounds, but that's not what this question is asking about. It's not saying what was the kid's weight at age 8. It's according to the model. So we're going to ignore what the actual data that was collected, and we're going to do exactly what they said and find, according to the red line, according to the model, what was the kid's weight at age 8. We did that before, so we're going back to our equation. We're going to plug in 8. We're going to get the predicted weight at 8 years. I got 63.2. 63.2 pounds. That is the Y hat, which again is what the model predicts, predicted weight, according to the model. Was it accurate? And it's pretty far off because the kid actually weighed 49.0, so the model was off. But that's the thing that happens with models. Even though this line is a pretty good indication of how this kid is growing, you're not connecting the dots. You need to show, you're using a linear model, so it might miss a point and it's going to be off from those. Therefore, it has what is called a prediction error. Each point will have a prediction error, and here I want you to find the prediction error of the model at age 8. And so we're going to go back to that equation that I gave you, but let's just make sure we understand. The prediction error, how far off was our prediction of the red line, our model, and the actual weight? 15 pounds-ish, maybe 10 pounds-ish, more than 10 pounds. Well, let's do it accurately because we also need to get the correct sign. I'm going to remind you of the formula. I erased it a long time ago, but it was error, prediction error. Lowercase e is a symbol for it, and it's y minus y hat. Now, let me use this space, limited space, to organize what we know. And it's very helpful for you to do this before prepping for it, so you know which one is which and you keep it straight. Y is the actual or observed value. Think about where we're getting that from. The actual weight of the kid at age 8. The table, labeled Y, age 8, 49.0 pounds. That's the actual weight. You can even write that into your notes. Actual or observed value is a more formal way of writing it, but I'll say actual. Y hat, that's your model. What does the model predict? The model predicted 63.2. We use Y hat in our model, so it kind of keeps it straight for us. 63.2 pounds. That's our model's prediction. And it was off by whatever the difference is, but we got to subtract it in the correct order and get the correct sign. It could be negative or positive. All right, Y minus Y hat. And it is definitely going to be a negative error. Negative 14.2 pounds. Okay. Now, okay. My graph is super bad. I gotta blow, okay, so I'm gonna erase this, I'm gonna blow it because I do want to talk about one thing, but I want to kind of focus on this. So that age 8 point is this one. So I'm gonna blow that up. That's actually not very accurate where I placed it because we'll see. Jesus, I'm way off. Okay. But let me just blow that up and exaggerate it. But I am trying to focus on that one point. You'll see in a bit. So I want you to graphically understand where that error is. So you can draw this, you can just draw, it's going to be a really rough sketch of it. Not all the details going to be present. But I am going to say age 8 and just focus on that. And there was the point. Let's say I did this super accurately or used software to do it and we were like focusing and zooming in. And there's our model. Okay. So looking at all the things we have over there, I still need that because I'm going to start talking about those numbers and where they are. So think about this. Think about what we did with that point. What is its value right here? If it was super accurate, what would that be right there? That was the point that we graphed from the scatter plot. So think about it. At age 8, that should be 49.0. I intended to place that dot at 49.0. I have to eyeball it on a hand-drawn graph, but that was my intention, to plot a point from the scatter plot of the data at 8, 49.0 among the other the other 3 points. Okay, but if I used age 8 and I went up like I did before where I was using the model to make predictions, right there, age 8, that's where the model hits it. Think about what this value is right here. I didn't place anything there, I just drew a line. I used 2 points to draw the line, but if it was super accurate, what would that value be? That's essentially taking 8 and plugging into the equation, which we did right here. That's your y hat. That's 63.2. The model predicts that when a kid is age 8, his weight's going to be up here at 63.2. For some reason, the kid was underweight, or what the model predicted at least, and so we were off. By how much? Negative 14.2 pounds was the error. That means this vertical distance right there That is your negative 14.2 pound prediction error. Okay. So how far off the data is from what the model predicts the line. Those are your errors. And every point had an error. Don't draw this one. But so this is a rough sketch and I'm going to redo it. It's not going to be the same as I did last time. I'm going to exaggerate. I had 4 points. They weren't, again, I'm exaggerating. Just to be clear, you don't have to draw this, but every point has an error associated with it, and that's going to be designated by those vertical lines. And we will see pictures like that where the errors are highlighted and sometimes labeled, and we will be working with those errors to do something in the next section. So those errors are important. We'll be able to compute them, but we also want to graphically understand that that's a vertical distance between points and the model, the linear model. Okay, I'm going to pause there. I'm going to talk about slope next. Okay, next is the slope of a line. Represents either the graph of it or the equation. Represents the rate of change in y with respect to x. Now, I am going to go back to, I want to have a standard letter for slope for the purposes of this little mini lecture, this part of this section. And if you recall, the two forms that I gave you had different slopes. Sometimes they use A for slope, sometimes they use B for slope. And I want to just make it consistent and not get that confusion. So I'm going to go back to our old algebra school of using M temporarily. Okay, so M is equal to the change in y over the change in x. And that symbol right there, let me write it in, signifies change in. And don't write this down, but I do want to mention that this form is, when you get familiar with it, that notation, change in variables to change in y over the change in x. If you actually worked it out, the change in y would just be subtracting two y values, two y coordinates. You could think about subtracting the y value of a second point minus the y value of the first point. And the change in x here, you would get that by subtracting two different x values. And you could subtract the x coordinate of a point 2 and the x coordinate of a point 1. And so that does represent your old school slope formula of y2 minus y1 over x2 minus x1. We're not going to be doing it that way because our points are not going to be nice whole numbers that we can work out a nice fraction with. They'll be uglier. And oftentimes we don't even do that. We'll get our calculator to do it, so we're not going to really emphasize that. But that does give you the slope formula, the old school slope formula. The only reason we're talking about it here is because I want you to get familiar with this notation, because we will be looking at change in y. But I do want to mention what that means in terms of rate of change. When x increases by 1, or is increased by 1 unit, whatever unit the units of x are, y increases by m units. Another thing I want to note that we will actually be using is if you rearrange this, you can rearrange it to get the change in y, a formula for the change in y. You would get that. We don't need to really get into the algebra of it, but basically if I want to cancel this change in x symbol, that quantity, I would multiply both sides by change in x and it would cancel, and I'd get the change in y by itself. And it would be equal to m times the change in x. Oops, I wrote it weird. Okay, but I don't want, so that's how you get it, but I just want you to be familiar with this. We will be using this Although I won't emphasize the formula, I'll emphasize a more intuitive way to interpret this concept. It'll be obvious once we get to examples, but we will be trying to compute the change in y. Okay, let's get to an example. And our example is going to be that model that we use to model the growth of that kid. All right. According to the model from the previous example, we mentioned that. Well, let me actually write it all up. Where x Okay, according to the model, the model we've been working with, y hat is equal to 7.2x plus 5.6, where x is the age in years. I just want to remind you of the context of that since I erased it. And y hat is the predicted weight in pounds. And this is according to the model, not the actual data that we gathered on the kid, purely based on this model. By what amount, according to the model? Will the child's weight change each year? Okay, so we're going to talk about that. It's not something I expect you to know now, although it is an answer you can just grab off the equation right away, and specifically hence it's a slope, but we'll get to it. I want to discuss it in more detail. I want you to understand it. So, and I'm leaving space here for a big picture because I'm going to illustrate it more graphically so you can visualize that line that I drew and the slope. So here's that model. And here is, according to the model, the kid weighs that much at a certain point in time. How much? I don't actually care. I'm not even going to draw an axis. But what I want to do is talk about what happens according to this model, according to this line and the equation right there. What happens 1 year later? And so, again, oh, maybe I should even draw it. I'll draw a half-assed one. Just to remind you of the axes, I'm not doing a lot of detail, but this was the age. You can barely see it, but I'm writing age along there. And this was the weight. And so, and I'm not going to mark any actual values because I really just want to focus on what's happening 1 year from one point in time. I don't care what age I'm talking about here. I'm not specifying any age, but whatever point that is that I started at, 1 year later is all I want to know what's happening each year. So 1 year later, he's going to grow. His weight's going to increase by how much? Well, our slope, and I'm using m again, is, where's our slope? What's the slope of this line? 7.2. I said we weren't going to use rise over run, but I kind of like, so I'm going to actually talk about it here. Oftentimes when you put things over 1, to think of it as a fraction. So I'm going to put 7.2 over 1. And now I'm going to remind you that slope is interpreted as rise over run. What's the rise? 7.2. What's the run? 1. Run is going left to right. Rise is going up or down. In the case of negative slope, it's going down, but here I kept it positive for now. You will be dealing with negative slopes later. Anyway, 1 year later, it's going up by 7.2 pounds. This is weight. That's a change in weight of rise for run, 7.2 pounds. So the answer here is just 7.2 pounds per 1 year. Let me write that in as a formal answer because it was a question, but I don't have any space for my answer, so let me clear some of this. was I doing? Oh, you gave me the answer. Okay, so the answer for this question is 7.2 pounds per year. That's the rate at which his weight is increasing. So a rate is often given as units that are something per something, and it's based on the fact that the 7.2 here, represents pounds. The one here, the run, represents whatever units of x is, 1 year. And this corresponds to me saying that when x changes by a unit of 1 year in this case, your y will change by amount m, 7.2. Okay, but anyway, your slope is crucial on how much it's increasing or decreasing by per year in this case. Let's talk about some follow-up questions. Where am I at? B? These are all going to be according to the model. We are abandoning the actual data for now and focusing on aspects of the linear model that we have. I'm going to write the next 2 questions up. I'm going to leave space for this one. A little bit of space. I got to do like 2 or 3 lines of computations first. Okay, sorry, I'm just writing, but I'll read off these questions. Our first, well, our part B, first questions that we have to deal with right now. Oh, I got to delete spinning space. B, according to the model, what was her predicted weight of the child at 4 years old? According to part C, our follow-up question, well, not follow-up because it's not related to that. According to the model, by what amount will the child's weight increase over a 4-year span? I'm going to erase this. But I'm gonna draw another picture, focus on certain aspects of that. Think about those problems as I erase. And actually, I want to rewrite this so I have space to do my computations right below it. Same question, I'm not editing it. Although I might word it differently because I forgot what I just wrote. According to the model, by what amount will the child's weight increase over a 4-year span? Something to that effect. You can leave it the way I wrote it. It's same. I might have just phrased it slightly differently. Okay. Graphically, I want to talk about the distinction between these two because you do see 4 years, 4 years. They are very different questions, though. I mean, you don't have to draw this. This is more to illustrate. I'll talk about, we're going to do computations to get these answers, but I do want to talk about the distinction between them. There's my model. Okay. First one is finding the predicted weight at 4 years old. So in this question, we're talking about a 4-year-old kid, age 4. Very early in the kid's life. And graphically, we would go up to the model, and we would get the predicted weight y hat. We'll do that. Part C, according to the model, by what amount will the child's weight increase over a 4-year span? They're not talking about a 4-year-old. They're not talking about any age in particular. They're talking about the kid being some age, some arbitrary age, I don't care what it is, I don't know where I place that, I don't care. But from that point, how much is the child weight going to increase over a 4-year span? So what I want to do is from that arbitrary age, I want to go 4 years later, and I want to see how much his weight changes or goes up by. For that question, I'm looking for the change in Y. I don't know where it is and I don't care because I don't know his age here. I want to know how much it changes over that 4-year span. From age 10 to 14. Or maybe not that. Maybe I want to go age 11 to 15. Or maybe we're doing it from age 20 to 24. It doesn't matter for a linear model, any 4-year span is going to have the same change in weight. And the emphasis there is we're not looking for the kid's weight. We're looking for the change in weight over any 4-year span. That's a distinction, and the distinction in terms of symbols is this one we're looking for y hat. And this one we're looking for the change in y. Okay, so now finding y hat, the predicted weight, we've done it several times now, it's just using the model. That gives the predicted weight of a kid at any age x. We're going to plug in 4 there, and we're going to do exactly what we did in earlier problems today with that same model. We've done this before with different ages. I got 34.4. Okay. That's right there, 34.4 pounds. Part C is new. We haven't really done this. We started to talk about change in weights, but we looked at the change in weight over 1 year. So if you recall, we did 1 year, and the kid went up 7.2 pounds. Oh, I don't know if you want to write this in. 1 year, 7.2 pounds. Okay, so intuitively, if the kid's weight is increasing by 7.2 pounds per year, without doing any equations or getting too fancy or anything like that, just intuitively tell me, 7.2 pounds per year this kid's growing. How much is he going to grow over a 4-year span if he's growing at a rate of 7.2 pounds per year? What would you do with that? You would multiply by 4. Essentially, graphically, I want to do those steps. So I don't know if I can fit it, but 1 year, it went up 7.2 pounds. Another year, 7.2 pounds. Another year, and another year. So I'm just doing 4 of those steps that I had earlier. So I'm just going to multiply by 4. 7.2 pounds per year times a 4-year span. Now, let me actually talk about that equation that I mentioned. I erased it, but I said that the change in y, and I said we would be using it. You don't have to write out the formula, you don't have to memorize it, or even really think about it in terms of those. You can do the intuitive notion of 7.2 pounds per year over a 4-year span. It's going to be taking that 7.2 pounds per year and multiplying it by the change in x. That's a change in time. It's not at 4 years old, it's just a change in time for 4 years. Again, from 10 to 14 or from 17 to 21 or any 4-year span. That's just a change in time of 4 years. Okay, you don't need to put units. You need units at the end of your answer. The only reason I'm putting it here is because I do want to talk about, you do have this cancellation of the units concept that you may have seen in chemistry. Pounds per year, years cancels, and your units after you do that will be pounds. Straight pounds, but you don't need to worry about that. I just wanted to mention that you do get this nice cancellation units, this proper cancellation in units. But ultimately your answer is 28.8 pounds, regular pounds. It's just a change in weight of 4 times 7.2. Okay, so again, you don't need to use this equation. You can do it intuitively. Just make sure you understand the distinction between this question and that question. This one is asking for the predicted weight, the actual full equation y hat. This one is asking for the change in weight, which you're going to be using just the rate of change, which was just the slope. The 5.6 does not come into play. You're not using that full equation there. Okay. Whew. I'm going to pause it here, and we're going to do one last example and wrap it up. Okay. Nothing too new on this one. A lot, we're going to go through the things we talked about previously. There's a couple little wrinkles. Data below. Shows the depreciation. Depreciate means to lose value. Of a car's value, specifically a car. I'm going to introduce variables. We're now going to get away from y and x and get you used to adapting a little bit. Let v be the value in thousands of dollars. And t, the years since 1990. You're going to be 5 years or 5 data points. I realize I'm going to have to make room because I'm writing big and killing my space. But I will make it work somehow. That's just with a dollar symbol, thousands of dollars. Okay. Suppose, hopefully you can see this. Yeah, we're good. Suppose we value the model with the equation v hat, so I'm using the hat on v this time, but that's still our model. It's v hat is equal to, and again I'm just giving you a model to work with. Later on, again, we will be learning how to come up with these models. But for this section, I'm just going to give them to you. Again, v's and t's instead of x's and y's. And let's see, okay, don't note the negative, negative 2.5 t plus 46.8. Okay. What is the predicted value in 1999 according to the model? So according to the model means we are ignoring the table, even if there's no 1999 there anyway, but even if there were, this is saying according to the model, so the table's irrelevant. The model's what we'd be using. Now, the additional wrinkle that I mentioned here is that you don't just plug in t, you have to make sure you know how v and t are defined specifically. V is the value in thousands of dollars. So this 33.9 means $33.9 thousand. This 24.5 means $24.5 thousand. T is a year since 1990. So you're not actually plugging in the full year, you're plugging in the number of years since 1990. So this is not your t values. Your t values, if you needed them, you would have to make an additional row, which you can put above it, and you have to figure out how many years it's been since 1990, your reference year. So they don't usually make equations where you plug in a full year of like 2018 because it makes it messy. They will often use what is called a reference year or a base year. And the way you figure out the t-values for that is to basically take your years and subtract 1990. Obviously, 1994, how many years since 1990 is that? 4 years. But to actually get that, in case it's not as obvious and not as nice numbers, you'd subtract, you'd find that difference. The actual year minus that reference year gives you 4. 1998 minus the reference year gives you 8. 2001 minus the reference year gives you 11, 13, and 15. So you're just subtracting the reference year to find that difference, or how many years it's been since that reference year. Okay. What is the predicted value in 1999 according to the model? And so let's use a model. T is going there, but again, we don't just plug in 1990 in there. We need a t value for 1999. So you have to use that reference year. You have to make sure you're plugging in the year in the correct way, not the full year, but the year since the reference year. That's going to be t is equal to 9. You plug in t is equal to 9 in for that. Oh, where's my calculator? Watch a negative. Again, you're using the negative symbol, not the minus symbol there. I got 24.3. Make sure you know what units these are. These are units of V, whatever V was given in. Thousands of dollars. B, according to the model, in what year will the value fall to $5,000? Yeah, $5,000. Okay, again, we're using the model. It's according to the model. Again, we have to be conscious about how we're plugging in the value or the year. I'm going to erase in a bit, but I'm going to write the full equation first, but I'm going to just rub out something and replace it. Okay, they want to find the year. Year's represented by t, or related to t. So they give us a value. Now here's an issue that comes up in the homework, and you have to be careful. We are not going to replace this with $5,000. That's going to give you a wrong answer. The reason is, you have to, just like with T, you need to be conscious of the way V is represented. V is in thousands of dollars. So this is $8.7 thousand. You don't see 8,700. So you need to be consistent with the way you plug in that value with the way the data is and the way the V is defined here. So you have to be consistent with this. So think about what you're going to plug in for V. It's related to this, but you're not plugging in 5,000. You're plugging in the number of thousands of dollars. So what goes there is just 5, not 5,000. So you have to be careful about that. Okay, from there we're good. That represents some value of $5,000. We're going to solve for T. T is not going to be our answer though. We need to convert it to a year, but we're good for now. We're going to first start solving this. I'm going to do it quickly. Okay, and I got, I'm skipping some steps. 16.72 is what I got. Now, you usually don't give decimal years. You don't say it's the year 2020.7, even though it's like we're well into 2020. You just round to the nearest year, and you don't have to worry about whether that's in the year 2020 or in the year 2019. I don't want you to get into what year you would call that. You would just round to the nearest whole number and then just convert it to a year. So we're going to round that to 17. That's still not the answer because 17 is not a year. It's not 2017, by the way. How do I get a year? Again, remember what t is. T is a year since 1990. And now you're going to go the other way. You're going to go from the t-value back to a year, and so it's 17 years after 1990. You're going to add back the reference year. Okay, and you get 2007, which looks reasonable because it was 8.7 at that year. And so 2007 is your answer. All right. So be careful about that, how the data is interpreted in the problem, how the variables are defined. Okay, where am I at? I'm going to erase all this, but I do need that data. Now we're going to jump back in. Where are we at? C? What amount is the value decreasing each year? Yeah, I don't know how to do the next problem over there. Okay, think about that. How do I know it's decreasing? Apart from the data, actually that's not even relevant. How do I know from the equation that the equation is predicting the value to decline? It's because your slope is negative, it's going down, and that slope is relevant to how much it's decreasing per year. Again, if you had a model, this is a real rough sketch, that's your linear model. You'd have some point in time, some year, and you want to know 1 year later how much it's going to go down by, and that's based on your slope. It's going down by negative $2.5 thousand for 1 year. That's it, that's your answer. You can put negative, I mean, technically it already says decreasing, so it's decreasing by $2.5 thousand per year. Negative, you can put a negative, I know what you mean. I'm not getting particular about the fact that it's, you know, double negatives or whatever, so that's fine. Negative 2.5 thousand or 2.5 thousand, either one is correct. I just want you to be able to get that value. Okay. What is the prediction error for 2001? Now here I'll pause and make sure you can do that and let you work it out. So I'm going to pause for a little bit, but I want you to pause the video and work this one out. I will mention that we're going to use a prediction error formula. I did give it to you in terms of y and x, or in this case just y. E is equal to y minus y hat. We're going to have to adapt it. So in place of y in your model, t is in place of x, v is in place of y, so it may help us to rewrite it as v minus v hat. It's still the same, the actual minus the prediction, the model's prediction, but we're just adapting it to a different letter than y. I will remind you, I just said it, but I'll actually write it out so you can visualize it. It is important that you remember which one is the actual and which one is a prediction. V will be the actual value, V hat will be the prediction based on the model, V hat. The model's even labeled with V hat to remind you of that. Where's the actual values coming from? The table. These are your V's. These are your V's here. The year, technically that's not your T's. Your T's we have to get by computing the, minus some reference year, but that's the idea. There's your V's, the actual values. And for the year 2001, what's the actual value? 21.6. What's the V hat value, the predicted value in 2001? We don't have it. We got to do it. We got to use that equation. Think about what you're plugging in for T, because you're not plugging in 2001. plug it in. 11. Clutter it too much. Okay, worked it out. Watch the negative, or don't forget about the negative rather. Get 19.3. And these are thousands of dollars, but nah, we don't need to put units yet. We will put it for our final answer. Let me rewrite that equation. V is 21.6. V hat is 19.3. And we get 2.3. And here's where I want to start including units. This is my actual answer. The prediction was off by $2.3 thousand. We predicted, the model predicts the value would be 19.3 thousand. It was actually, the actual value when they looked it up online or whatever was 21.6 thousand. So our model was a little bit off, but still pretty close. It's a good model. We don't have a graph to go with it, but I assure you it's a decent model. What am I doing now? Okay, so now that we've gotten familiar with the concept of prediction errors, I want you to calculate the prediction error for each year. So for every single data point. We just did this one, but you have 4 others you want to do. What are we going to do? We're going to grab this value for V. We're going to use this T and plug it into the V hat formula right here and then subtract. What are we doing for this one? We're going to grab the V here. We're going to plug in that T into the equation, subtract. We're going to do the same thing over and over. So instead of doing it 4 separate times or even 5 separate times, we're going to do it in the list feature, because the list feature, again, is good for doing some computational, the same computation over and over for every single data point. So we're going to start making a table. I'm going to need this space, but I need to glance at that first. So keep in mind our variables. The key thing is going to be the variables that we need for a thing. We need T's, we need V's, we need V hats. We don't need the full year. So we're going to start with T and V. Generically, we would start with X and Y, and then work from there. We're going to use T and V, but that is like X and Y. And so we need the T values, because what we did here was plug in T values. So I'm going to need the 4, the 8, and so on. And then the V's are the actual value, 33.9. So these first 2 columns are just going to be our actual data set. Well, sorry, with the T values instead of the year. I'm going to erase this. I have the data over there, but make sure you have it down somewhere, because I just need the room to actually make this table. I need that model too. What do I have? 11, 13, and 15. So go ahead and put that into L1, L2. We need to build up to errors is what we're going for. And I do want you to do this in the list. In theory, you could just do this 4 times. It's not that bad. But we are going to be building off of that and doing something more complicated. And you're going to have also more data points to deal with. So this is something I do want you to do it in the list feature, even though it may seem to be not bad to do it that way. But no, we need to do the list for future efficiency. Okay, so keep in mind what I did. Are we ready? If not, pause it. We took our V, which I have there. To get the E, we needed a V hat, and then we subtract. That's going to be our E. So I need to figure out the V hat. The V hat is different for every single year. V hat is equal to 2.5 times T plus 46.8. So the V hat for 1994 will be different from 1998. So we'll be taking these T's and plugging them in there. So I definitely want to call for V hat. Let's think about how we're going to do that. How do we do it over here? Here's my V hat right here. How did I get that? I use this equation. And what do I do with the equation? I plug in each T. So I want to take 4 and plug it in there to get V hat. I want to take 8 and plug it in here to get V hat. 11, plug it in there. 13 and 15 into there to get all 5 V hats. They're all different. Okay, and I should space up here for my formulas, but you got that down. I'm just making some room so I can write formulas and talk about what we're doing. My T's are in L1. Or in substitute, that would be like X's in L1. My Y's are in L2. In this case, my V's are in L2. In L3, I just said what we want to do, so think about what we're going to do in there. To get the V hats. Right here. This is how you can beat V hat. So I want to take each T and plug it in here. So I want to use this formula. I want to do negative 2.5 times T, which are all in L1. So I'm going to do negative 2.5 times L1 for the full formula plus 46.8. Just like I did here with the 11, but I want to do it for the 11 and for the 8 and the 4 and the 13 and the 15. So I want to do it all at once in the list feature. Column header of L3 and follow that model. Negative 2.5 times L1 plus 46.8. And by the way, as you do this, we should be able to see these values should pop up on this row right here. 11, because we did it for 11 already. Let's see. I got, oh damn this glare. Oh, it just blinded me. 36.8. 26.6. Oh wait, what does that say? 26 point. Oh, let me just look over here. 26.8. 19.3. Boom. That's the one we already did by plugging in 11. 14.3. And 9.3. That's our V hats. What do we actually want? We want the prediction error for every point. E is equal to V minus V hat. So we're good. One more step. E, which again is V minus V hat, or Y minus Y hat. Okay, so think about what I want to do. What did I do with V and V hat right here? I subtracted them, and I got 2.3. So I want to do V minus V hat in L4. Think about what I'm going to do for the formula. Make sure in the column header, V, which is L2, minus V hat, which is L3, and subtract that minus that, that minus that, that minus that, and so on. L2 minus L3. I got negative 2.9, negative 2.3, positive 2.3. We already did that one. That confirms that we're doing it correctly. 3.0, or just 3. And negative 0.6. Okay, and that's it. So those are our errors. Again, we're done for this section. Don't stop the video yet. The reason I'm having you do this is because we're later going to do something in the next section actually, where we do the squares of these errors and sum it, and we get what's called the sum of squared errors, which is a useful thing. So we are going to come back to this very example to do the sum of squared errors, but for now we just wanted those errors and getting used to the concept and also getting used to doing in the list. Real quick, you don't have to draw this. We're done with your notes at least. I do want to make sure we understand this would be a downward sloping model. How do I know that? Because it's a negative slope. and I would have a point there. This is exaggerated. Point there, point there, point there, and a point there. So our data set would look something like this. This is exaggerated. I just want to be clear, because we are going to be talking about this later, that all these vertical lines represent how far off the data is from the model. So those are all the errors associated with the data set. Every single point has an error. We just computed them all. What's this error? This would be for the year 4, 1994. This is year 8. Again, this is not accurate. This is just giving you a rough picture. I just want to make sure you understand where things are coming from. What's that distance right there? That's an error for the 1994 model of negative 2.9. That error right there is negative 2.3. That one is a positive 2.3. That one is a positive 3, the biggest error so far, and this one is a negative 0.16. Okay, so all those differences between the point and the model is the difference between this, which is what the prediction errors are. So we are going to be looking at a picture like this and doing something with those errors. So we need to get familiar with the fact that these errors, prediction errors that we compute, are graphically these vertical line segments from the points, data set, to the model. Okay, that's all I got. Okay.